Okay, let's unpack this. Have you ever had that moment? You're interacting with an AI, and it gets you. It doesn't just answer your question, it remembers what you said 5 minutes ago.
And not just that, it can pull in knowledge from, years of data at the same time.
Exactly. It feels so seamless, almost like magic. But underneath, there's just this whirlwind of activity happening in the blink of an eye.
And that whirlwind has a name. It's called context engineering. It's really the entire operational framework that lets these systems give you those dynamic, context-aware responses.
It's more than just looking something up in a database.
Oh, much more. Think of it as a high-speed management system for knowledge, for actions, and for memory itself. And all of that ultimately dictates how good the answer is that you get back.
So our mission today is to basically give you the blueprint for that. We're going to walk through this critical 8-step process.
The entire cycle.
The whole thing, from the second you hit enter to the moment the answer pops up on your screen. This is your shortcut to understanding how all these pieces, memory, tools, agents, how they all connect.
And it's helpful to think of it as the agent's thought cycle. It's super managed, highly concurrent. It all starts with your trigger, your input, and then it immediately splits off to pull from two different kinds of memory.
And then it might use some specialized tools.
If it needs to, yeah. And only after all of that does the agent put everything together to synthesize that final coherent answer.
That sounds incredibly complex to manage in real time. But let's follow the assembly line. It has to start somewhere. Step 1, user input.
That's the ignition point. It's the trigger. Could be a simple question, could be a command like run a financial model.
Anything, really.
Anything. But whatever it is, that input tells the system to stop listening and start acting. It's the command to kick off this whole 8-step process.
Okay, so the moment that input is received, the system fires up step 2, short-term memory.
Right, or STM. The input is immediately logged and stored right there.
And the key detail here, the thing we really need to drive home, is that this STM is, by design, temporary.
Completely. It's volatile. It's only meant for the current session. I like to think of it as the digital version of sticky notes on your desk while you're on a tough phone call.
Right, just for quick reference.
Its function is pure speed and, conversational coherence. If you ask a follow-up question, the system doesn't need to go back and reread everything. It just glances at its sticky notes, the STM. That's what makes the dialogue feel so fluid.
So that raises a question for me. Why does it need this separate temporary scratch pad at all? Why not just have one giant single memory? It feels like an extra layer of complexity.
Well, the reason is really about efficiency and cost. Long-term memory is huge, and it's highly structured.
For deep knowledge retrieval.
Exactly. And querying that massive structure for every little follow-up would introduce a ton of lag, huge computational overhead. So SPM acts as this low-cost, high-speed buffer. It lets the system pretend it's just having a quick focus chat.
Because it can recall the last few things you said instantly, without having to search the whole library.
You got it. So we're sacrificing persistence for speed.
That makes a lot of sense.
Yeah.
So while the system is scribbling notes on its temporary pad, it's also doing something else at the same time. Step 3, the long-term memory check.
Correct. This is a parallel operation. So while STM is the context of this conversation, LTM holds the persistent stuff, the deep knowledge base.
And this data, it's coming from external databases, or the sources mentioned something called MCP servers.
Yeah, that seems to be a term for their own proprietary data management systems. The point is, it's the permanent archive.
So what's that LTM check actually doing? Is it just a keyword search?
No, it's much smarter. It's usually doing what's called a vectorized similarity lookup. The system takes your query, and it generates an embedding for it.
A mathematical representation of its meaning.
Exactly. And it uses that to very quickly find semantically related chunks of data from, millions or even billions of documents. It's looking for stuff that's related in meaning, not just by keywords.
So it could be a policy document, a tech manual, or even a conversation you had 6 months ago that's related.
That's the power of it.
Okay, so STM gives us the immediate conversational thread. LTM gives us the background knowledge. But what if they conflict? Say, I asked about policy A yesterday, which is an LTM, but now I'm clearly asking about policy B in STM.
Great question. That prioritization is the real art of this, which we'll get to in a bit. But for now, just know the system retrieves both. It just stacks it all up for the agent.
So it's like, here's the recent stuff weighted for recency, and here's the old stuff weighted for relevance.
And it's up to the agent, the final orchestrator, to decide what's most useful.
All right, before we get to that decision, there's another step. The system might need its utility belt. Step 4, action tools.
Yes, exactly. If just retrieving information isn't enough, maybe you need a calculation or you need to interact with the outside world, the agent needs specialized tools.
These are like pre-built functions it can call on.
Pretty much. They're API wrappers or dedicated code environments. They let the agent go beyond just retrieving knowledge. It's the difference between saying, tell me about the stock price, and go get the latest stock data, calculate the 90-day moving average, and make me a chart.
And the sources gave some really cool examples here, executing Python code, rendering diagrams, but the one that stood out to me was X-ray analysis on data. That sounds really specific.
It is, and it's a great example. It's not a medical X-ray, of course.
Right.
It refers to deep data structure inspection. So when the agent pulls data from some external source, say a huge, messy JSON file, it needs to check the structure and make sure the data is clean before it uses it.
So quality control check.
An internal audit, exactly. It ensures the agent isn't basing its final answer on bad or incomplete data.
That's a serious level of detail. So the tools give the agent its real power. Now we have all the ingredients: recent context from STM, deep knowledge from LTM, and maybe some output from the action tools. This all leads to the big moment, step 5, context to prompt.
This is where the agent truly earns its keep. It acts as the ultimate editor. It takes your original simple query and it enriches it, contextualizes it, using both short-term and long-term memory.
How does it actually do that? Does it just staple everything together?
It's more systematic. It's often a process of token injection. The agent has a template, and it will literally stuff the most relevant context from STM and LTM into the prompt before your actual question.
So my simple question might become this huge detailed instruction.
Exactly. The final working prompt might start with something like, based on the user's prior request about policy B from STM and historical data showing 3 previous revisions from LTM, answer the following question.
So it's no longer a generic question. It's a highly specific, custom-built instruction set that must make the output way more precise.
It's the whole point. Without that step, the agent is just guessing based on its general training data. This step ensures it understands your specific intent right now.
And once that perfect prompt is built, we get step 6, the short answer to the user. This is the part we actually see.
Right. The output is synthesized directly from that super detailed prompt. The response is based on everything we've talked about. The memories, the tools, the external data, all of it.
The sources emphasize that the answer is usually concise. Why concise? Wouldn't a really detailed answer be better?
It comes back to efficiency again. Concise answers mean lower latency, less computation, and honestly, they're easier for us humans to digest.
We want the nugget of information, not a data dump.
Precisely. The system's goal is to give you a sufficient, immediate solution because it already did all the heavy lifting in the background.
Right. But it doesn't stop there. The process loops back on itself with a learning cycle, starting with step 7. User expands short-term memory.
Absolutely. The system is always adapting. When you provide your next follow-up, your next query, that new input immediately updates the STM. It refreshes that temporary context.
So every correction, every new question, is keeping the agent up to date with the conversation. If it couldn't do that, it would just forget what it told you a second ago.
It would fall apart instantly. But here's the final, critical piece that ensures the system gets smarter over the long haul. Step 8. The upload to periodic memory.
This is the retention mechanism. Okay, so if STM is temporary, how does it decide what's important enough to keep permanently in LTM? There must be some kind of filter.
There is, and it's key. This isn't just a bulk data transfer. Only relevant short-term memory data gets periodically uploaded to long-term memory.
How does it define relevant?
It uses relevance scoring. It looks for unique insights or generalized information or maybe a really complex task that it handled successfully. It might summarize an entire interaction before it creates that new memory chunk for the LTM.
So it's not saving the user asked about their vacation on Tuesday. It's saving the insight, like the user consistently shows a preference for high-altitude travel.
Precisely. It's about retaining high-value generalized information. And that process is how the system builds a larger context base for the future. It's how it gets smarter and more efficient over time.
And that closes the loop. So to recap this whole framework of context engineering, it starts with your user input, which goes into short-term memory.
While at the same time, the system is checking long-term memory.
Then the agent might use its action tools. All of that gets combined and filtered in the context to prompt step.
Which then produces the short answer that you see.
And then your next input, expands the short-term memory, and finally, the cycle completes when the most important bits are chosen for the upload to periodic memory.
That entire highly coordinated dance is the foundation. It's what ensures these systems feel intelligent and context-aware. And, it's why they evolve based on your interactions. You're actively helping build their long-term memory.
Which leaves us with a final kind of provocative thought to chew on. If the system's permanent knowledge, its LTM, is built entirely from these periodic uploads, meaning only the highest scoring, most relevant bits are saved.
And the main goal of that filter is efficiency.
Right. What does that imply about how the agent's knowledge base develops? If it's only saving what's relevant to certain tasks, is that specialization also creating blind spots? Or even, internal biases over time?
You have to wonder what all that efficient retention might be leaving out.